Forget oil. The most strategically dangerous machines on Earth print features smaller than a virus. If their supply chain fractures, the shock reaches data centers, cars, hospitals, weapons, and power grids. This is the Silicon Shield, a world protected and threatened by the same extraordinary concentration of chip-making power.
Semiconductors are not one commodity. They are a hierarchy. Mature chips regulate brakes, batteries, appliances, and industrial motors. Leading-edge logic and high-bandwidth memory drive artificial intelligence, secure communications, and advanced weapons. In 2025, processes at 7 nanometers and below generated 74% of TSMC's wafer revenue. The important question is no longer who owns the most silicon. It is who can repeatedly manufacture the most difficult layers, at scale, with acceptable yield.
That capability remains geographically concentrated. TSMC's 2025 report lists 4 12-inch megafabs, 4 8-inch fabs, and a 6-inch fab in Taiwan, while its new 2-nanometer process entered high-volume manufacturing there late that year. This concentration helped inspire the phrase Silicon Shield, the argument that the world's dependence on Taiwan raises the cost of conflict. But dependence is not a force field. It may deter disruption or make every crisis more consequential. That uncertainty is the shield's central paradox. At the technical core sits extreme ultraviolet lithography. ASML's machines use light at 13.5 nanometers to pattern leading-edge chips. The light begins when a carbon dioxide laser strikes microscopic tin droplets, creating plasma up to 100,000 times each second. Conventional lenses would absorb this wavelength, so the beam must bounce through precision, multi-layer mirrors developed with Zeiss. One weak link in the source, optics, stages, metrology, vacuum, control software, or specialist supplier network can stop the process. And one popular claim needs correcting. Neon is important to parts of the wider laser gas supply chain, but modern EUV makes its working light from tin plasma, not a neon lamp. Governments are responding by paying to duplicate capacity. The United States allocated tens of billions of dollars in chips manufacturing incentives, and in 2026, its Commerce Department described semiconductor investment commitments in the hundreds of billions. Europe says its first CHIPS Act mobilized more than 52 billion euros, yet still left key dependencies in advanced manufacturing and design. In June 2026, the Commission proposed CHIPS Act 2.0. Reshoring is real, but it is not instant independence. A fab needs tools, chemicals, power, water, trained teams, customer volume, and years of process learning before construction becomes reliable output. The supply chain is fragmenting at the same time. American export controls now reach advanced computing chips, high-bandwidth memory, manufacturing equipment, design software, and certain support activities. The rules also keep changing. In January 2026, the United States shifted selected accelerators, including NVIDIA's H200 and AMD's MI325X, to case-by-case license review for approved customers in China. That is not a clean technological wall. It is a moving boundary designed to slow military-relevant capability without severing every commercial connection. The result is a technology Cold War fought through thresholds, licenses, and supply chain due diligence. No country can copy the frontier by cloning one machine. Chip power now comes from a system. Transistor architecture, chiplets, advanced packaging, high-bandwidth memory, design tools, and the software that maps a design onto a particular factory. TSMC began volume production of 2-nanometer nanosheet technology in late 2025 and plans further variants in 2026. Europe opened its nano-IC pilot line in February 2026. Backed by a €2.5 billion investment to test technology beyond 2 nanometers. Sanctioned markets will keep finding workarounds, but each workaround must still solve yield, reliability, throughput, and ecosystem scale. The physical cost is easy to hide behind the word digital. A United States environmental assessment found a median annual energy use of roughly 2.74 million megawatt-hours across a sample of 29 fabs, and median ultra-pure water use of about 4.25 billion gallons. Lithography, etching, deposition, Cleanroom air, vacuum, gases, and wastewater treatment all consume resources. The next frontier may combine specialized AI accelerators, three-dimensional packaging, photonics, and eventually quantum components. But every gain in compute still lands somewhere, in a fab, a grid, a watershed, and a political bargain. So the world's most contested resource is not silicon alone. It is the ability to coordinate thousands of precision steps across a trusted network, then repeat them millions of times. The silicon shield may reduce the appetite for war, yet it also concentrates global risk inside a small number of companies and places. Nations can spend staggering sums to build resilience. They cannot purchase decades of learning overnight.